Welcome to The Explainer. Today, we are cracking open one of the oldest and maybe the deepest cold cases in all of science. For centuries, the most brilliant minds have been chasing this one single, elusive suspect. And the truth they found? Well, it completely rewrote our understanding of reality itself. And that big central question, it sounds so simple. What is light? But let me tell you, the answer is anything but simple. This is the story of that investigation, a detective story really, into the true identity of light, a mystery that took literally hundreds of years to solve. Okay, so our story kicks off way back in the 17th century, and right away the investigation zeroes in on two main suspects. Each one was backed by a real scientific heavyweight, and this right here set the stage for a debate that would rage for over a century. And here are our two main suspects. It's fascinating, really. You have these two totally opposing camps. In one corner, you've got the one and only Sir Isaac Newton. He was convinced that light is just a stream of tiny, fast-moving particles. He called them corpuscles. But then, in the other corner, you have the Dutch physicist Christian Huygens. He had a completely different idea. Light is a wave, a pressure wave, moving through some kind of mysterious, invisible stuff he called the ether. So for, over 100 years, there was a clear frontrunner in this investigation. And let's be honest, when Isaac Newton says something, you pretty much listen. His reputation was just enormous. So the particle theory, it was basically accepted as fact. But there were these nagging little clues, things that just didn't quite add up. The case was definitely not closed. All right, let's fast forward now to the early 1800s. A new detective enters the scene, a British physicist named Thomas Young, and he comes up with this brilliant, absolutely ingenious experiment that would just blow the whole case wide open. This was the first piece of, shocking, irrefutable evidence. And his experiment really gets to the core of the whole mystery. Think about it. If you shoot solid particles, like tiny little BBs, through two slits, what do you get? You get two simple bands on the wall behind them, right? Makes total sense. But if you send waves, like water waves, through those same two slits, they interfere with each other, and you get this really complex pattern of many light and dark bands. So, the million-dollar question was, what would light do? And Young's experiment showed, with zero doubt, that light created the exact same interference pattern as the waves. And after that discovery, the evidence for the wave theory just started piling up. It was like an avalanche. First, you have the French physicist Augustin Fresnel, whose work not only confirmed what Young found, but he made this incredible, kind of crazy prediction. He said there should be a bright spot of light right in the middle of a solid object's shadow. I mean, it sounds completely absurd, right? But guess what? It was true. And then, fast forward to the 1860s, James Clerk Maxwell comes along and unifies electricity and magnetism, and boom, his equations describe light perfectly as a self-propagating electromagnetic wave. So, by the time the 19th century was wrapping up, the investigation was pretty much over. The scientific community had reached its verdict. The evidence was just overwhelming. Newton, it seemed, was wrong. Huygens was right. Case closed, light is a wave. But you know how these stories go. Just when everyone thought the mystery was solved, the file was closed, a really strange new clue surfaced. And it came from a completely different area of physics. It was something the wave theory, for all its success, just could not explain. And it threatened to overturn the entire verdict. This new puzzle was called the photoelectric effect. So what scientists saw was that when you shine a light on a piece of metal, it can actually knock electrons loose. Sounds simple enough, right? But the details presented a massive problem for the wave theory. Okay, so here's the problem. According to the wave theory, a brighter light, a more intense wave, should have more energy, right? So it should knock out electrons with more energy. But that's not what was happening, not at all. Experiments were showing that a dim blue light could kick out really high-energy electrons, while a super bright red light might not eject any at all. It turned out to be the color of the light, its frequency, that mattered, not its brightness. And the wave theory? It had no answer for this. It was totally stumped. And then, in 1905, this young, basically unknown patent clerk decides to take a look at the century-old cold case. His name was Albert Einstein. And what he did was resurrect a suspect that everyone thought was long dead and buried. So Einstein comes along and proposes that light isn't a continuous wave at all. He said it's actually made of individual, separate little packets of energy, almost like tiny bullets. He called them light quanta, but we know them today as photons. And this idea, it explained the photoelectric effect perfectly. See, a single photon of blue light just has more energy than a photon of red light, so it can knock an electron out with a much bigger punch. Just like that, the whole case was thrown into complete chaos.
I mean, this was the ultimate contradiction, right? You have the double-slit experiment, which proves beyond a shadow of a doubt that light is a wave. And then you have the photoelectric effect, which proves just as convincingly that light is a particle. Both experiments worked. Both sets of evidence were true. So how? How could light possibly be two completely different things at the exact same time?
Well, the final verdict in this long, twisting investigation wasn't going to be either or. No way. The answer was something far stranger. Something that forces all of us to accept a totally new and frankly bizarre vision of reality.
The astonishing answer is, it's both. Light is both a particle and a wave. This is what we call wave-particle duality. It acts like a wave when it's just traveling through space. That's why it creates that interference pattern. But the moment it interacts with something, the moment it hits matter, it acts like a particle, which is why it knocks out electrons one by one. It's a wave and it's a particle. It all just depends on how and when you look at it. But here's the thing. Solving the mystery of light's identity, it only opened the door to an even deeper, even stranger puzzle about the fundamental nature of our universe. A puzzle so bizarre that even Einstein himself, the very person who helped create it, just refused to believe it could be real. This next concept is called quantum entanglement. And the idea is that two particles, say two photons, can become linked. They get connected in such a way that they essentially become a single system. And what happens to one of them instantly affects the other. And when I say instantly, I mean it, even if they're on opposite sides of the entire universe.
Now, Einstein, he could not get on board with this. It just seemed to fly in the face of his own theory of relativity, which says, that nothing, not even information, can travel faster than the speed of light. He hated the idea so much, he called it famously spooky action at a distance. He was just convinced that quantum mechanics had to be incomplete.
But the story doesn't end there. Decades later, a physicist named John Bell came up with a theoretical work to actually test this. And then, in the 1980s, Alain Aspect and his team ran the experiments, and they proved it, beyond any doubt. The spooky action is real. On this one point, the great Albert Einstein was wrong. Our universe really is at a fundamental level interconnected in this very strange, very spooky way. And that leaves us with one final, truly mind-bending question, one that comes from the work of physicist John Wheeler. Think about this. If we observe a photon from a star that took, say, 1 billion years to get here, does our choice to measure it right now somehow decide the path it took all that time ago? Does reality actually wait for us to look at it before it decides what to be? That is the lingering mystery that this amazing detective story of light has left for all of us to try and solve.